It is hard to imagine our world without the moon. It lights our way at night. We look at it through telescopes. We draw it. But we rarely think about the huge role it plays in the life of the entire planet. And if our partner suddenly packs up his things, closes the door and goes to his mother, or disappears forever, then trouble awaits the Earth. Hi everyone. If werewolves are watching us right now, you might like this scenario, but everyone else probably won't. It's our channel, if you haven't already guessed. So what would happen if the moon disappeared? And is such a scenario possible? Now let's find out. Let's get started. Origin of the moon. Let's first look at how we utilized such a beautiful satellite. There are several theories on this. Daughter, the hypothesis that the moon separated from the ancient Earth due to centrifugal forces. Spouse, the assumption that the moon passed close to our planet and was captured by its gravitational field. A related version, in which the moon and the Earth were born at the same time and only grew together. This sounds like some kind of family chronicle. However, the giant impact theory is now considered the most likely theory. It states that Theia, a celestial body the size of Mars, collided tangentially with the poor Earth, shedding much of the mantle from its surface. This substance, together with the debris of Theia, formed the moon, and our planet received a parting tilt relative to the Earth's axis. Will it fall, or will it fly away? The satellite orbits around us in a circular spiral. While it was much closer to us in the distant past, it is now gradually moving away. The moon is moving away from the Earth very slowly, about 4 centimeters per year. Will it ever be able to break that relationship? No, that won't work. Our satellite is gradually slowing down, and in 5 billion years, the radius of the moon's orbit will reach its maximum. And then the moon starts to get closer to the planet again. But that doesn't matter, because then the sun will become a red giant that will grow and push both the moon and the Earth out of orbit. Well, could our satellite fall on us? Theoretically, yes. The moon and the Earth slow down on their axis. And 50 billion years later, they find themselves in mutual spin-orbit resonance. Simply put, they face each other on the same side. The centrifugal force of gravity compensating for our planet no longer affects the satellite, and it will finally fall in about 65 billion years. But you remember the red giant, right? There's just no time for something like this to happen. A magical disappearance normally. The moon could disappear just at the wave of a magic wand. But we'd like to fantasize about what would happen if we lost our partner right now. We all know that the moon is responsible for the ebb and flow of the sea. It forms a kind of bubble, 2 humps of the world ocean, one to the moon, one on the opposite side. Without the influence of a satellite, this bubble would burst. Huge waves flood the coast. Water is sprayed evenly across the surface of the planet. And when all this storm subsides, the tides we're used to will no longer exist. The water level continues to change under the influence of the sun, but very little. This, of course, affects both the life of the ocean's inhabitants and the climate. But there's still flowers. Much more dramatic changes are caused by the instability of the tilt of the Earth's axis. The angle of tilt is currently 23.5 degrees, and it provides the usual seasonality. This means that when the North Pole is tilted toward the sun, it's summer in the northern hemisphere, and 6 months later, at the other end of the Earth's orbit, the North Pole is away from the sun. Jon Snow is screaming that winter is coming, and it's getting cold. Without the moon, the tilt of the axis would change by tens of degrees, and completely unpredictably, the climate will begin to change. After a severe drought, it snows. and after rain it suddenly warms up. All in all, hypertensives and weather people can only sympathize. The moon also regulates the speed of the planet's rotation, and therefore the length of the day. When it disappears, and the day is only about 6 hours long, there is no work or sleep, and constant hurricane-force winds blow, sweeping away everything in its path. Frankly, the weather for the next million years is completely non-flying. In addition, the sun simply does not have time to heat the surface of the Earth during these difficult daylight hours, and the result is an ice age. Sharp fluctuations in axial tilt and changes in rotational speed cause the tectonic plates to move. We should expect earthquakes and volcanic eruptions all over the world. Motion. The Earth's magnetic field is created by the movement of molten metal in the core. The moon flattens and expands the planet's surface, and that movement keeps the core quite warm. Our satellite disappears, and the core begins to cool, stop, and finally solidify completely. The magnetic field disappears. What does this do? Look at Mars. It lost its magnetosphere over 4 billion years ago, turning into a scorched red desert, and the cherry on the cake of disaster. Without the moon, our natural and necessary defense against meteorites is weakened. But there is some good news. When the moon disappears, we see a starry sky. Now the light from our satellite is damaging our vision. Without it, we'll see a lot more stars in the sky. Yay! You can admire this wonderful play. Between food wars, of course. If the moon had never existed. Anyway, our world is largely the way it is because we have the moon with us. But what if it never existed? Can life on Earth be as diverse as it is now? Could we reach such heights of civilization? If the theory that the moon was formed by the collision of the Earth with another planet is true, then that means that if this had not happened, all of the Earth's crust would still be in place, and tectonic plates would not exist per se. The surface of the Earth will be monolithic, meaning there will be no mountains or hills. Precious metals, such as gold, platinum, and rhodium, would also be unavailable to us. They fell from the surface of Theia to Earth in a cosmic impact, and then seismic activity dropped them closer to us, and we were able to mine them. Without these metals, beautiful earrings and spaceships would be forgotten. But there would be someone on Earth who could wear jewelry and launch rockets into space. This question is rather difficult to answer. If life had originated on such an inhospitable planet with no fixed seasons, plagued by monstrous winds, and bombarded by asteroids, it would have taken a very different path in its development. Without the tidal wave, the sea dwellers would probably never have reached land. More complex life forms would have had a much lower probability of arising, which meant that humanity would have been unlikely to exist. If we were born, we would probably have tails, gills, and fins. All in all, it is hardly right to call these creatures human beings. And that's all for today. Thanks for watching, sweethearts. Okay, our satellite isn't going anywhere from us right now. We can still enjoy romantic moonlit walks, build conspiracy theories about the existence of aliens, and dream that one day we will repeat that small step for humans and one giant leap for humanity on the surface of the moon. There hasn't been a single day in the last few million years when the sun hasn't risen above the Earth. Our star rises every day and then sets at sunset, and we all know that very well. But what would happen if the sun suddenly disappeared for 24 hours? What will happen to humans, animals, plants, and society as a whole? Will we be able to survive, or is this the end of the world? We will try to answer all these questions in this issue. So sit back and let's go. So let's imagine that the sun suddenly went out. Obviously, the first thing we would notice is that the world would become very dark, as there would no longer be any natural sunlight. At first, we will be able to see many stars and even planets in the dark sky, as there will be no light pollution from the sun. There is even an upside to this, because astronomers will be able to see many different stars that were previously invisible through telescopes. Nevertheless, paradoxically, we will not be able to see the moon, because without the sun's radiation, its surface will not be reflected. So we should not rely on our natural satellite as an additional source of light. We have also noticed that solar energy negatively affects artificial satellites and satellite communications. So at first, it's not so bad, because in the first hours after the sun disappears, we have very fast internet and smartphones work much better. But this will not last for long. The next obvious consequence of the sudden disappearance of the sun is a sudden cooling. As you know, we get our heat from the sun. So when our star goes out, the Earth gets colder. In the daytime, the air temperature can sometimes drop to 0 degrees Celsius. In principle, it is something similar to the air temperature at night, because it is known that it is always quite cold at night. But during the first 24 hours after sunset, temperatures vary in different parts of the world. For example, colder regions are even colder than usual. And in hot countries, the temperature does not reach 0 degrees Celsius. However, even in the hottest countries, it is quite cold. Fortunately, when the sun disappears for just one day, we are saved by the greenhouse effect. Simply put, the greenhouse effect is a phenomenon in which the sun's heat is retained in the lower atmosphere. This is actually a long-term effect, and the temperature rise in the lower atmosphere does not happen every day, but gradually over many years. But even that is enough to keep humanity from freezing too quickly. But I don't think 24 hours is enough time for the life of the entire planet. Let's talk about oxygen. We all know that humans and animals need oxygen to survive. A planet without oxygen is considered uninhabited and uninhabitable. During the day, without sunlight, people start to run out of oxygen. And that's because without sunlight, photosynthesis of plants is impossible. As you probably know, plants begin the process of photosynthesis when the temperature is warm and sunlight is available. They absorb carbon dioxide and produce oxygen. Fortunately, when the sun is gone for only 24 hours, the lack of photosynthesis is not a big problem. On average, we inhale about 1 kilogram of carbon dioxide a day. So we manage with the rest of the oxygen in a little more than a day. However, if the sun disappears for a long period of time, all the oxygen will be burned up, leading to the death of humans and animals. The next thing that happens when the sun goes out is a sudden increase in electricity consumption, which is also quite obvious, because mankind is deprived of a natural source of light, so they have to rely only on electricity. On the other hand, this won't help those people who have solar panels installed at home, as they will find themselves completely without power. It's worth noting that many power plants around the world also use solar panels. So when the sun goes out, many neighborhoods are simply left without electricity. However, I believe that a short-term disappearance of the sun would have little effect on the ruling elites of many countries, as very powerful auxiliary devices are often installed under government buildings. Autonomous power generators, but not when the sun disappears, but when other energy sources fail. It is worth noting that a surge in electricity consumption can have a negative impact on power plants, as they are not designed to handle excessive loads. Because of this, power plants can experience accidents and many outages. Financial markets and industries will also suffer from the disappearance of the sun, as people will probably panic and start withdrawing money from their bank deposits and accounts. which could hit the fortunes and capital of many global companies. Continuing on the topic of companies, I would like to add that many of the world's companies depend on solar energy, as absurd as it may sound. For example, the factories of many companies are powered by the aforementioned solar panels. So the disappearance of the sun could lead to the financial collapse of many companies. In addition, many stock exchanges simply shut down. So of course, even short-term losses have a very negative impact on the global economy. Workplaces, schools, and universities are also closed. The disappearance of the sun is, of course, hotly debated by journalists, and it becomes a major issue. A few hours after the disappearance of the sun, panic and mass hysteria sets in. People are incredibly scared because they don't know that the sun just hid during the day, like it does in our area. Believers probably think that Judgment Day is upon us. Riots begin in the streets. People are frantic, smashing cars and buildings, looting and ransacking stores. In addition to incredible fear, people also experience severe depression because the natural sunlight acts as a natural mood enhancer. A few hours after the sun sets, leaders of countries make appeals to their citizens to reassure people. I advise them not to panic and to remain calm. However, the leaders of the countries themselves are probably shocked by what is happening, so they hide in their shelters and try to survive. Supposedly, chaos and anarchy will break out in countries, and citizens will be left to fend for themselves. I guess to each their own. So let's imagine that everything is finally over, and the sun has reappeared in the sky. What happens in this case? And what are the consequences of this hypothetical phenomenon? First of all, people are feeling a huge relief because the sun is coming back. Temperatures will gradually normalize. Factories will start producing oxygen again. Factories and businesses will open, and industry will start working again. The economy is also recovering, and may even survive the recovery. However, many people are still afraid. Depression affects many people, which is not surprising considering what everyone went through during those horrible 24 hours. One way or another, eventually everything will go back to normal, and mankind will forget the sunny sky like a terrible dream. But what if the sun disappears forever and never returns? Consider this sad scenario. With no sun for more than a week, temperatures drop below 0 degrees in all regions of the Earth. As a result, most animals and insects die, causing the food chain to collapse. In a year without the sun, the Earth's temperature will rise to -100 degrees, which means that all life on Earth will perish, including mankind. The pull of gravity also disappears, causing our planet to jump out of orbit and fly off into space, as scientists believe. We can only hope it never happens. We also hope that our star will not leave us without light for a day, because as you can see, even a few hours without the sun is catastrophic. And as a bonus, we offer you a look at another hypothetical scenario. As we know, strong solar flares can have a negative effect on our planet. However, this negative effect often manifests itself mostly in the form of power and electrical outages. But what if a massive solar storm hits Earth, the likes of which humanity has never seen before? Let's watch this together. Let's make it clear right away that we're not talking about an ordinary solar flare, but an actual solar storm. In other words, from a geomagnetic storm. We are talking about the possible collapse of large amounts of electromagnetic radiation and clouds of hot plasma onto the Earth, ejected by the sun. The source of a geomagnetic storm is a so-called coronal mass discharge. So, in 2012, a powerful geomagnetic storm entered the Earth's orbit, fortunately due to the rotation of the sun itself. The active region that caused the eruption was not directed directly at the Earth, and the geomagnetic storm that followed the eruption was just a side effect of this eruption. On the whole, things went well, as we avoided a direct hit. In 1859, however, things were much worse. At that time, a powerful geomagnetic storm hit the Earth, causing telegraph systems to fail across Europe and North America. And some telegraph poles even caught fire from the massive radiation flux. To think, at that time, telegraphs were the pinnacle of technological development. Now the whole world is based on electronic technology. So imagine the consequences if such a geomagnetic storm were to hit the Earth. It all starts with a massive explosion on the surface of the Sun. The Earth was being subjected to a massive electromagnetic pulse. Such an explosion would disrupt the signal between Earth and orbiting satellites. A few hours after the explosion, charged particles begin bombarding the Earth's magnetosphere and destroying artificial satellites. A few days later, the energetic plasma cloud finally reaches Earth. Why is the universe exactly 13.799 billion years old? Why is our solar system exactly 4.5 billion years old, and not, say, 6 billion or even 600 million? How do you know the age of the universe and the Earth, the solar system, and the Milky Way galaxy? Surely many people have thought about this question, which has been of interest since ancient times. But this question could only be answered by modern science, and only recently. Until the second half of the 18th century, it was believed that the universe was eternal and unchanging. Then, based on the analysis of biblical texts, it was believed that the creation of the world took place in 3,929 years before Christ. Only in 1787, French naturalist Georges Leclerc concluded that if our planet at birth was a ball of molten iron, it would take 75 to 168,000 years to cool down to its present temperature. That is, he estimated the age of the Earth and the Sun on the basis of physical models. After 108 years, Irish mathematician and engineer John Perry recalculated the thermal history of the Earth and determined its age at 2 to 3 billion years. At the very beginning of the 20th century, Lord Kelvin came to the conclusion that if the Sun gradually shrinks and shines solely by releasing gravitational energy, the age of our star, and therefore the maximum age of the Earth and the other planets, could be several hundred million years. But at that time, geologists could neither confirm nor refute these estimates because of the lack of reliable methods of geochronology. In the middle of the first decade of the 20th century, Ernest Rutherford, an American chemist, Bertram Boltwood, developed the basics of radiometric dating of Earth rocks, which showed that Perry was much closer to the truth. In the 1920s, mineral samples were found whose radiometric age approached 2 billion years. Later, geologists increased this value many times, and by now it has more than doubled to 4.4 billion. Additional information can be obtained from meteorites and meteorites. Almost all radiometric age estimates are between 4 and 4.6 billion years old. Modern helioseismology allows us to directly determine the age of the Sun, which according to the latest data is 4 to 4 billion years. Since the duration of the gravitational compaction of the protosolar cloud was measured in millions of years, we can safely say that no more than 4.6 billion years have passed from the beginning of this process to the present day. At the same time, solar matter contains elements much heavier than helium, which were formed in the thermonuclear furnaces of massive stars from previous generations that burned in supernovae and exploded. This means that the extent of the universe far exceeds the age of the solar system. To determine its excess, we must first go into our own galaxy, and then beyond. The lifetime of our galaxy can be determined in different ways, but we will limit ourselves to the two most reliable. The first method is based on the observation of the glow of white dwarfs. These compact and initially very hot celestial bodies represent the last stages of life of almost all but the most massive stars. To become a white dwarf, a star must burn all of its thermonuclear fuel and undergo several cataclysms. For example, becoming a red giant for a while. A typical white dwarf is composed almost entirely of carbon and oxygen ions embedded in degenerate electron gas, and has a thin atmosphere dominated by hydrogen or helium. Its surface temperature is between 8,000 and 40,000 degrees Kelvin, while the central zone is heated to millions or even tens of millions of degrees. According to theoretical models, can also be born dwarfs, consisting mainly of oxygen, neon, and magnesium, which under certain conditions turn into stars with masses from 8 to 10, 5, or even up to 12 solar masses. However, their existence has not yet been proven. The theory also states that stars with at least half the mass of the Sun appear as helium white dwarfs. There are many such stars, but they burn hydrogen very slowly, and so live for tens or hundreds of millions of years. Since the white dwarf cannot resist fusion reactions, it glows due to stored energy, and therefore cools slowly. It is possible to calculate the rate of this cooling and the time required for the surface temperature to fall from an initial temperature of about 150,000 Kelvin for a typical dwarf to the observed temperature. Since we are interested in the age of the galaxy, we should look for the longest lived and therefore the coldest white dwarfs. Modern telescopes can detect galactic dwarfs with surface temperatures below 4,000 Kelvin and brightness 30,000 times lower than that of the Sun. But so far, nothing or very little has been found. It follows that our galaxy cannot be older than 15 billion years. Otherwise, its number would be detectable. This is the upper age limit. What can we say about the base? The most elegant white dwarfs known to date were discovered by the Hubble Space Telescope in 2002 and 2007. Calculations have shown them to be from 11.5 to 12 billion years old. To this, we must add the age of protostars from 500 million to 1 billion years. It follows that the Milky Way is no younger than 13 billion years old. The final estimate of its age, based on observations of white dwarfs, is about 13 to 15 billion years. This is the first method, and this is the second. It is based on the study of globular clusters of stars located on the periphery of the Milky Way and rotating around its core. They contain hundreds of thousands to more than 1 million stars bound together by mutual attraction. Globular clusters are found in almost all large galaxies, sometimes numbering several thousand. There are almost no new stars born there, but there are plenty of old ones. About 160 such globular clusters have been registered in our galaxy, and perhaps 2 to 3 dozen more will be discovered. The time of formation of the oldest globules allows us to set a lower limit on the age of the galaxy. It's technically very complicated, but it's based on a very simple idea. All the stars of the cluster, from supermassive to the lightest, formed from a single gas cloud, and therefore were born almost simultaneously. Over time, they burn up their main hydrogen reserves, some sooner, others later. At this point, the star leaves the main sequence and undergoes a series of transformations, culminating in either a complete gravitational collapse, with the subsequent formation of a neutron star or black hole, or the formation of a white dwarf. Therefore, studying the composition of a globular mass allows us to determine its age quite accurately. To obtain reliable statistics, the number of clusters studied should be at least a few dozen. Observations of the 41 globular clusters in our galaxy have shown that their average age is 12.8 billion years. Our galaxy, however, must be older than its mass. Its first supermassive stars exploded as supernovae and pushed the nuclei of many elements, especially those of the stable isotope of Birol 9, into space. When globular stars began to form, their newborn stars already contained beryllium, and more were born later. The concentration of beryllium in the atmosphere can be used to determine the youth of galaxy clusters. As data from the NGC 6937 cluster show, this difference is between 200 and 300 million years. Therefore, we can say that the Milky Way is more than 13 billion years old, reaching perhaps 13th March 2013. 4 billion years. This is almost the same estimate as the estimate from observations of white dwarfs, but it is obtained in a very different way. But how did they know the age of the universe itself? It was not until the beginning of the second quarter of the last century that this question became scientifically possible. In the late 1920s, Edwin Hubble began determining the distances to dozens of nebulae outside the Milky Way that just a few years earlier had become independent galaxies. These galaxies are moving away from the Sun at a radial velocity measured by the redshift of their spectra. Although the distances to most galaxies were determined with a large error, Hubble still found that they were roughly proportional to the radial velocities. 2 years later, he confirmed this conclusion based on observations of other galaxies. Some of them are more than 100 million light-years away. This information formed the basis of the famous formula known as Hubble's law. dV is the radial velocity of the galaxy with respect to the Earth. D is the distance, and h0 is the proportionality factor. In 1927, Georges Lemaître showed that the general theory of relativity allowed the expansion of galaxies to be interpreted as evidence of the expansion of the universe. 4 years later, he had the courage to take this conclusion to its logical conclusion by hypothesizing that the universe originated from a virtually point-like embryo, which he, for lack of a better term, called an atom. This primordial atom could have remained in a static state for any length of time up to infinity, but its explosion produced an expanding space filled with matter and radiation, which in a finite amount of time gave rise to the present universe. From this work of Lemaître, and later works of both Hubble himself and other cosmologists, it followed directly that the age of the universe, naturally counted from the initial moment of its expansion, depends on the value that everyone now calls Hubble time. The nature of this dependence is determined by a particular model of the universe. Assuming we live in a flat universe full of gravitational matter and radiation, Hubble's time must be multiplied by 2/3 to calculate its age. This created a mystery. Hubble measurements showed that the universe was born 1.2 billion years ago, which clearly contradicts the already then largely underestimated age of the Earth. This difficulty can be overcome by assuming that galaxies move more slowly than Hubble assumed. Over time, this assumption was confirmed, but it never solved the problem. This contradiction was generally resolved in 1998 to 99, when two teams of astronomers proved that for the last 5 to 6 billion years, outer space has been expanding at an increasing rather than decreasing rate. This acceleration is usually explained by the fact that in our universe, there is a growing influence of anti-gravity, the so-called dark energy, whose density does not change with time. The duration of the universe with an anti-gravity component does not have to be equal to 2/3 of Hubble time. Therefore, the discovery of the accelerating expansion of the universe, which won the Nobel Prize in 2011, resolved the disconnect between cosmological and astronomical estimates of its lifetime. It was also the prelude to developing a new method for determining his birth date. On June 30th, 2001, NASA launched the Explorer 80 probe into space. It is able to detect temperature fluctuations in the microwave background radiation at an angle of less than 0.3 degrees. The fluctuations in the cosmic microwave background radiation, or more simply, the outliers, are due to fluctuations in the density of the electron-photon gas that once filled the cosmos. When this temperature change fell close to zero, almost all of the free electrons fused with the nuclei of hydrogen, helium, and lithium, thus creating neutral atoms. Before that, however, sound waves propagated in the electron-photon gas and were affected by the gravitational fields of dark matter particles. These waves left a trace in the cosmic microwave background spectrum that can be interpreted by the theoretical apparatus of cosmology and magnetohydrodynamics. According to the latest calculations, its most likely duration is 13.799 billion years. Thus, astronomers who have estimated the age of the universe in 3 different ways have gotten fairly consistent results. So now we know, or rather we think we know, when our universe was born, at least with the accuracy of a few 100 million years. Who knows? Maybe one day our descendants will include the solution of this ancient mystery in the list of the most important achievements of astronomy and astrophysics.